In this first section of chapter 2, we're going to kind of go back to probably what you learned as the definitions of these different trig functions in geometry class, because we're going to talk about the right triangle-based definitions of these trig functions. So if you look at the graph given to you, we'll say that this is your angle theta. Angle A is going to be your angle theta. And if we're comparing the sides of this triangle created to angle theta, we would call the side length y the side opposite to angle A, and we would call this side length here, x, the side adjacent to angle A, or our angle theta. So this idea of an x and y coordinate around your coordinate grid does lend you back to the definitions you had in geometry class when you looked at these for a right angle. So if we extend this out a little bit and kind of refer back to the image here and the definitions we used in chapter 1 for these trig functions, we can rewrite these definitions in regards to a right triangle. So for sine of theta, this would be your opposite side over y, which in this case, if we're looking at a right triangle, not y, I'm sorry, r would be your hypotenuse. And for cosine, since it's x divided by r, that would be your adjacent divided by hypotenuse. And last but not least, tangent would be y over x, which we have renamed as the opposite over adjacent. Now the three other trig functions, since again they are reciprocals of sine, cosine, and tangent, we can just flip those definitions just like we flipped the letters. This would be hypotenuse over the opposite, the hypotenuse over the adjacent, and cotangent would be the adjacent over the opposite side. So how am I supposed to remember all of this? Great question. This is when we do throw it back probably to an acronym you learned in geometry class, which is SOHCAHTOA. SOHCAHTOA stands for sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. And tangent is the opposite over the adjacent, SOHCAHTOA. If you can remember the first three trig functions, you just remember which is reciprocal of which, and then you have the other completing the full 6 trig functions. So if we apply this to an actual triangle with numbers, and we have this image here, we want to find the sine, cosine, and tangent values for A and B in the figure. So both for A and for B. We'll start off with A. So I'm gonna highlight A in purple here, so we know we're talking about this function. So if we are going to find the sine of A, we know that the sine of A is the opposite over the hypotenuse. Well, the side length that is opposite to that one is going to be 7 over the hypotenuse, which is 25. The cosine of this angle A is going to be the adjacent side length, which is 24, over the hypotenuse, which again is 25. Now, last but not least, tangent of A would be the opposite over the adjacent. So if I look comparing angle A to its opposite side, which was 7, over its adjacent side, which is 24. If we change which angle we're using, so this time we're not using A, we're focusing on B. This time looking at angle B, it'll just switch which is opposite, which is adjacent. The hypotenuse should stay the same always. So if this time we're finding the sine of B is opposite over hypotenuse. This time the opposite side length is 24 and the hypotenuse is 25. The cosine of angle B would be the adjacent, this time is 7 over the 25 for the hypotenuse. And your tangent of angle B would be the opposite of that angle, which across that triangle there is 24, and the adjacent is 7. Now what I want you to notice before we leave this page is that some of these values, some of the answers we got on this page are the same. For example, sine of A is 7 over 25. Cosine of B is also 7 over 25. Interesting. Cosine of A is 24 over 25. And sine of B is 24 over 25. Interesting. In fact, there must be some relation between sine of A and cosine B, and cosine A and sine of B. That relationship is called cofunctions. So if we're looking at this diagram here with angles A, B, and C, notice that whenever we're going to draw a triangle, we're going to let the two side lengths that are shortest be A and B and our hypotenuse be C, so that Pythagorean theorem holds, which also means we're going to label the angles with capital letters across from that side length. So across from A is capital A, across from B is capital B, and across from side length C is capital C. So C is my right angle. That's going to be what we're using. And just like we noticed on the front, we noticed that these were the same because they're the same ratio. So these are called cofunctions. Since they're cofunction pairs, we can find a relationship between their values and between their angles. They are called complementary. Now in chapter 1, when we talked about complementary, that means that they need to add up to 90 degrees. So in our triangle above, we can say that angle B is just 90 degrees minus angle A. And since we've established that sine of A is equal to cosine of B, we can substitute in this value here, 90 minus A, right here for B, and we get the first of our cofunction identities. Sine of A is equal to cosine of 90 degrees minus A. Now there are 6 cofunction identities that I'm going to have you memorize, so this is going to be something that will potentially be on your formula quizzes, so you can tell me what the cofunction identity is for each of these. But we can use each of these cofunction pairs and cofunction identities to write functions in terms of other functions. For example, cosine of 52 degrees can be rewritten with its cofunction. Cosine has a cofunction with sine as long as we do 90 minus that angle. So 90 degrees minus the 52 degrees from cosine of 52 degrees, we can say that this is identical to sine of 38 degrees. 90 minus 52. For tangent, its cofunction is cotangent. So we know that tangent of 71 is the same as cotangent of 90 degrees minus 71 degrees. So we know that this is equal to cotangent of 19 degrees. Based on the definitions shown above, secant's cofunction is cosecant. So we can rewrite secant of 24 degrees as cosecant of 90 minus 24 degrees. 90 minus 24 is 66, so this is the same as cosecant of 66 degrees. So we're just rewriting them in terms of their cofunction. But what we can do with these cofunctions is actually use them to solve complicated identities. We're going to find one solution for each equation and assume all angles are acute angles, which just kind of keeps us in realm of what we're learning about today. So if we have cosine of theta plus 4 degrees equal to sine of 3 theta plus 2 degrees, I know that these two functions are cofunctions, which means that their angles are complementary. Complementary angles must add up to 90 degrees. So all I'm going to do is take the angle measurements out of cosine and add the angle measurement from the sine and know that this has to be complementary or equal to 90 degrees. Now, we are solving for the theta. That is the unknown variable here. So this is what I'm trying to get by itself. We go back to old school algebra skills as if that was an x variable. We combine like terms, we see that there are 4 thetas plus 6 degrees on the left side of this equation. We would subtract 6 degrees from 90 degrees, we get 84. And last but not least, divide both sides by 4 so that theta would be equal to 21 degrees. Voila, we have found a solution for this equation. Pause the video right now and attempt question B on your own just to make sure you understand how these functions are involved. Since tangent and cotangent are cofunctions, we know again that their angle measures must add up to 90 degrees. So I just take these angle measurements, add them together, and set them equal to 90. Remember, we are solving for theta here. That is an angle. I forgot my plus sign. And beep, boop. Okay. So we combine like terms. This would be 3 theta And then the 18s are going to cancel out actually, so this is actually really easy. 3 theta equal to 90 degrees, divide by 3 on both sides. That means theta is equal to 30 degrees. And we found our angle measurement. As we saw in chapter 1, the values of these trig functions will change as your theta is changing or as your angle is changing. That's the variable in these terms. So let's talk about some patterns we're going to see within these different thetas and as theta changes. So if we look at these images here, this theta has gotten bigger each time. This is a small angle, medium angle, big angle. Let's think about the relationship between the two different things. If we're thinking about sine is going to be y divided by r. In this triangle, we have a small number divided by r. Then we have a medium number divided by r. Then we have a large number divided by r. Since our numerator is increasing and our denominator, our radius, is staying the same, that means that my number is getting bigger. So as a increases from 0 to 90 degrees, sine of a increases. If we look at the x value here for this triangle, we start off with a really long, then a medium, then a short x value. Since that number is getting smaller and the radius is staying the same, cosine of a is going to decrease as we go from 0 to 90. If we think about tangent, since tangent is the relationship between these two terms, we have small over big, medium over medium, big over small. Therefore, those fractions are increasing in size, so tangent of A is also going to increase. Now, the reciprocals do not exactly follow suit. Since we are changing denominators for the reciprocals, as A increases, cosecant of A is actually going to decrease, secant of A is going to increase, and cotangent of A is going to decrease. Now, why this is important to know is because it allows us to give a quick check on some of our work here. In example 4, we're going to compare function values just to make sure that we know what should be bigger, what should be smaller. So we're going to determine whether each statement is true or false. For the first one, we say that sine of 21 degrees is greater than sine of 18 degrees. But we know that in quadrant 1, sine is going to increase. So we know that this number with a bigger theta should be bigger than this number. That means that this is a true statement. So a bigger theta for sine means a bigger value for sine. But for B, it says that secant of 56 degrees is less than or equal to secant of 49 degrees. But we know secant should be increasing, so this is false. Because if it's increasing, the bigger angle should have a bigger value, so that inequality sign is flipped the wrong direction. There are some really special and really common angles that we're going to need to know the trig function values for. Let's discover them, and then we'll fill in this table of values that I'm going to want you to have pretty much memorized, at least the first 9 spots here. It says find the 6 trig functions for the value of a 60-degree angle. So we're putting this back in a triangle, which means we can use the geometry definitions, the right triangle definitions for the 6 trig functions. If we do the sine of theta, or the sine of 60 degrees, which is what we're doing, sine of 60 is going to be the opposite over the hypotenuse. But remember, this is your opposite, your adjacent, your hypotenuse when it comes to 60 degrees. So the sine of 60 degrees is going to be square root of 3 over 2. The cosine of 60 degrees, which is the adjacent over the hypotenuse, is going to be 1 over 2, 1/2. And the tangent of 60 degrees is the opposite over the adjacent, which is square root 3 over 1. Or more simply, just square root 3. For the reciprocal values, yes, you can go back to the triangle definition. I just find it easier to look at the 3 we've already done and just use the reciprocal of those, which means I'm going to look at cosecant of theta, or cosecant of 60, and it's going to be 2 over square root of 3, but I'm going to rationalize that denominator and make that 2 square root of 3 over 3. The secant of 60 degrees is just going to be the flipped over version of cosine, which in this case is just 2. And then the cotangent of 60 degrees is, again, the reciprocal of tangent, but when we rationalize that denominator, it'd be square root 3 over 3. There we have our 6 trig functions. Now, if you've taken trig before, specifically if you've taken my pre-calc class before, you'll notice that these are some of the values I had you memorize before for the special right triangles in your 45, 45, 90, 30, 60, 90 triangles. We're still going to have to know some of these values because a calculator will return to you only a decimal approximation of these instead of an actual value. So I'm going to want you to know these just like it's the back of your hand. You can either draw pictures of triangles and create this table or memorize the table itself. We're going to take a pause when we do this table. We're going to put a pause right here because if you can know the first 9 tiles here, the other 9 tiles are easy because they're just reciprocals of these values. So we filled out the 60 degrees already. We said that that was square root of 3 over 2, and then 1/2, and then square root of 3 over 1. If we do this same thing, looking at this triangle for 30, I'm referring to this triangle here, sine is the opposite over the hypotenuse. Well, opposite of 30 is 1, hypotenuse is 2. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, which would be 1 over square root 3, but we're going to rationalize that denominator and make it square root 3 over 3. For a 45, 45, 90 triangle, which might be helpful to draw over here if you have a little bit of space or on a separate sheet of paper to draw yourself a 45, 45, 90 triangle. Now, if that's the case, we know that around a typical circle, let's say that this is angle 1, or sorry, side length 1, this would be side length square root 2 due to Pythagorean theorem. For the 45, 45, 90 triangle, if this is my 45 degrees, sine would be opposite over hypotenuse, which would be 1 over square root 2, but we're going to rationalize that denominator to be square root 2 over 2. Cosine of theta would be the same, square root 2 over 2. Tangent would be opposite over hypotenuse, which would be 1 over 1, which is just 1. Now again, these 9 would be very, very helpful for you to have memorized because you can just very easily pop over the reciprocals. We'll do the reciprocals in order, so we'll start with the reciprocal of sine, which is cosecant. That reciprocal, 2 over 1. For the 45 degrees, the cosecant is just going to be square root 2. And for cosecant, it's going to be the reciprocal of 60 degrees. Secant is the reciprocal of cosine, again 2 square root 3 over 3, and then your root 2, and then your plane 2. Cotangent, the reciprocal is root 3, 1, and square root 3 over 3 when you rationalize that denominator. Now there are some patterns here that you might start to notice in regards to both the first basic 3 and then the reciprocal. Some things that I notice is that when you look at sine, the numerator goes 1, 2, 3, all divide by 2. Cosine goes 3, 2, 1, all divide by 2. And tangent, it is a little bit different, but if you remember that 45, 45, 90 means that the tangent of 45 is 1, it's pretty easy to remember these other two. Now this is something that would probably be a part of your daily formula quizzes. I will probably put a blank thing like this and ask you to fill it out because again, these come from here. So if we can remember these first 9, then we have all 18.